Oh,
I did it. I did it. Yeah, it's a recording.
Okay. All right. Can everyone see the screen? Okay, so I'm going to talk about our work on EPR microresonators, and some of the work I'm going to talk about is old work which was published last year, and I'm going to present some newer perspectives and insights and some newer work results that we've gotten in the past year. So what I work on is miniaturizing the resonator in EPR spectroscopy. The resonator, we know, is one of the main enabling technologies in EPR spectroscopy, which makes it possible to get detectable signals from weak samples. The resonator that we are that all of us are most familiar with is perhaps a rectangular cavity or a dielectric resonator or a loop gap resonator of some sort. These cavities have active volumes of about 10 to 100 microliters. So that's the amount of sample that you need, that you should ideally have in order to get the maximum possible signal. And this is especially important if you have dilute samples. So the sample quantity can be thought of in two terms. One is the sample amount itself and the sample concentration. And so what we want to do is miniaturize the resonator so that it can measure small samples, but also at small concentrations. So in this talk, I'll start by sort of delineating some broad application spaces for microresonators. I'll talk about challenges in microresonator design. And during this, I'll go through some previously reported microresonator designs and what they provide and what they don't provide. Then I'll talk about the planar inverse anapole microresonators, which is our attempt at tackling this problem. And I'll explain how this design provides advantages in terms of operability, scalability, and cost effectiveness. And then I'll end with a future outlook and where we might be headed. Okay, so the first application space for these microresonators is for precious biomacromolecular samples. For example, we work with a collaborator who work on melanopsin. And so this is a GPCR that's extremely difficult to express in adequate quantities. For example, I was told that a sample for CWEPR required, I think, 100 or 120 plates to make, and then if they want to do DIR on this sample, they'd have to make 240 plates, and this amounts to sample preparation work of several weeks, and it's it's a daunting task. And so if we can reduce the amount of sample required for EPR measurements of membrane proteins, especially because proteins like this can't be crystallized, and EPR becomes a very important part of the structural biology toolbox in providing information about conformation and dynamics. This is the first sort of application space where microresonators can be very impactful. So this is the information that I'm sure everyone's familiar with, that we can get from regarding spin-labeled proteins. And we would like to get the same information from sub-nanoliter samples or nanoliter samples. So what are the desired microresonator characteristics if you want to study such samples? Well, the first is if we can get an active volume of less than a microliter, and the concentration sensitivity should be what is possible with macro resonators, or if it should be equal, if not better than the concentration sensitivity that's available right now. So we should be able to go at least down to 10 micromolar concentration sensitivity. This is for CWEPR. In pulse EPR, there are a couple of more requirements, which is that you should have an active volume which has a homogeneous microwave excitation field over it, and it should have a high power to field conversion ratio so that we can get short pulses, and the pulse length applies to the entire volume of the sample being studied. The other application space is microcrystals, where if you want to do single crystal studies to get, for example, orientation dependence measurements, so that you can get a complete characterization of the spin Hamiltonian. And there's a beautiful paper by Jason that was published in 2019, where they did this on nanoliter sized samples by using a self-resonant microhelix. But there are some samples that are even smaller. For example, I work with a collaborator who works on perovskite oxides, and they're usually obtained as polycrystalline materials, and the single crystals in these polycrystalline materials are usually a picoliter and typically even smaller than a picoliter. So if we want to do single crystal measurements on such, and again, these materials are very difficult to grow as larger single crystals. So if we want to speed up materials research, and if we want EPR spectroscopy to help in this regard, then we should be able to tackle single crystal measurements on picoliter or smaller samples. So this is a very challenging task. But it is an important application space for EPR microresonators, especially because dopants and defects EPR is one of the most important techniques to study dopants and defects in such materials. And again, the desired microresonator characteristics over here would be, since we are going to concentrate more on CW measurements, then we want to be able to confine the B1 to a very small point or a very small volume of less than a picoliter if possible. And we should have also a pretty high concentration sensitivity if you want to detect dopants and defects. The third application space is in surface samples, for example, epitaxial films. And again, if we want to study dopants, so dilute samples in epitaxial films. So this is an interdigitated resonator that was reported a few years ago. And you can see that the extent of the resonator it's pretty wide, but the resonator probes only the spins in a layer of thickness 150 nanometers below the resonator surface. So we want a large surface area extent, but we want to confine the B1 in one direction right? So we want to confine the B1 along the vertical direction with a large coverage in the X and Y directions. And of course, we want a large concentration sensitivity, a pretty high concentration sensitivity, or a low concentration sensitivity limit. And the fourth application space is miniaturizations. So the idea of using permanent magnets for making miniature EPR spectrometers is pretty old. It's been reported. The first idea was reported, I think, more than a decade ago. And this is possible in EPR because the static field homogeneity requirements are much less stringent than, for example, in NMR. And so we can get away with using permanent magnets. But over here in the two sort of compact ESR spectrometers that are available, that I could find in the present day, they use glass tubes of 2 millimeter in internal diameter. And so if we can reduce the sample size even further, then that would enable more compact spectrometers. And that essentially lets you put the ESR spectrometer out in the field, and it really broadens the scope of EPR applicability by not limiting, by not limiting ESR to only those researchers who have access to a spectrometer, to a high-end spectrometer. Okay, so if we want to make an impact on all these application spaces, then we need to think about what affects the resonator sensitivity. So this is all, this is a pretty old analysis from Fair's paper. It's 1957. The signal to noise ratio, in terms of resonator characteristics, the signal depends on two main factors. One is the fill factor, or the filling factor, which is eta, and the second is the quality factor. And the filling factor can be broadly or simplistically thought of as the ratio of the sample volume to the active volume of the resonator. But in fact, we need to think about it more subtly. For example, it's not just about making the resonator small, it's also in some cases tailoring the B1 confinement so that it fits the sample of your choice. For example, sometimes, as we said, in thin films, we might not need a confinement in all three directions. We might need confinement in only one direction with wide coverage along the surface. So it's about tailoring the active volume to your required application space. And again, the resonator sensitivity then depends on the fill factor. And the Q factor. The Q factor is again dependent on, has a fill factor dependent term in it. If you look at equation 3b, you'll see that, and if you compare equation 2 and equation 3b, you'll see that there is an intrinsic sort of contest between the eta and Q, so that as we increase eta, the Q decreases automatically. But this is for energy that's being dissipated by absorption from a paramagnetic sample. Right? So this is magnetic dissipation. There are also other avenues of energy dissipation, and so mostly dielectric losses, and those and dielectric, ohmic, and radiative losses. And those are what those losses are what we're going to tackle in order to improve resonator sensitivity. But we can see that the resonator sensitivity can be qualified in terms of two parameters: the fill factor and the quality factor. Okay, so this is the rectangular cavity that we're also familiar with, and it has the active volume at the center where we place the sample of about 100 microliters. And it can be represented as a lumped circuit, so a self-resonant circuit which resonates at a certain value of inductance and capacitance. And a physical direct physical representation of this lumped circuit is the loop gap resonator, which is basically a cylinder with a slot cut into it, and the slot acts as the capacitor and the cylinder acts as the inductor. And so you have a loop gap resonator, which was reported, I think, in the 1960s. And when you, so this has an active volume of 1 microliter, so that's great. But you can go to real extremes in squeezing down the active volume even further. And what allows us to do this is the process of photolithography, where we can just deposit pretty much any arbitrary shape of microstrip on a dielectric substrate. And we can go to really small dimensions, thereby allowing very small active volumes. So you can go to 1 nanoliter and even tens of picoliters. So all this is, the established work in microresonator design. So let's get familiar with the main problem with in microresonators, which is the radiating electric dipole. So if you see, this is an omega type resonator. It has that loop, if you can see in figure B. What I have highlighted is the capacitive gap that's next to the loop, and you can see that the electric field is concentrated in that capacitive gap. So there are two problems with this. First is that this, when we squeeze the microresonator down to such small sizes, the ohmic losses and radiative losses from that capacitive gap become pretty high relative to the size of the structure. And so the radiating electric dipole is one of the main problems. And the second is that in these, because all the elements in the lumped circuit are squished together, there's you have very improper separation between the electric field and the magnetic field regions, and that causes further losses from lossy samples such as aqueous samples. So what are the challenges in microresonator design? First is maintaining Q, because the increased losses from that capacitive gap result in a loss of Q factor, which deteriorates sensitivity. Another consequence of a poor quality factor is that you can't couple to feed lines very easily. And so it's difficult to record the signal, the reflected power coming back from the resonator. The second challenge is scalability. So the design should be scalable over a broad range of frequencies. Now, this is not so much of a problem at high frequencies, because at high frequencies, the resonator sizes are automatically very small because the wavelengths are small. And so the active volume is not a problem. But you should have scalability from, let's say, if you want to go from 3 gigahertz up to 90 gigahertz, your resonator size should be scalable so that you can do multi-frequency measurements. The third problem, and this is a difficult problem, which is controlling confinement and shaping the excitation field to your sample, to your application. And the fourth challenge is how to not make these resonators so expensive that they just become prohibitive to use. So I'll tackle each of these challenges and how we have tried to solve them, or how the planar inverse anapole resonator solves these to a certain extent. So the first, maintaining Q while confining B1. Okay, so as I said earlier, there are 3 types of losses from a planar microresonator. In this case, a planar microresonator is basically a metallic structure deposited on a dielectric substrate. And we do this because we can get very small feature sizes of less than 100 microns by doing this. But from such structures, we have 3 types of losses: dielectric, resistive, and radiative. So the resistive or ohmic loss can be overcome to a certain extent by just going to a lower temperature so that the ohmic losses decrease. That decreases the overall operability of your EPR spectrometer, because it's not very useful if you can only operate it at low temperatures. The second is the dielectric loss, which is if your microwave is going through the dielectric substrate, then it shouldn't be absorbed in the dielectric substrate because it's lossy, right? And a great way to overcome this is by using low loss substrates. And so Blank did this by using, for example, LSAT or lanthanum aluminate, which are very low loss. They have very low loss tangents. And the third kind of loss, which had not been addressed in previous literature, was the radiative loss, which, as I said before, an oscillating electric dipole, it radiates energy, and so that's another dissipative mechanism that leads to losses, which in turn leads to a lowering of the Q factor. So we were advised by a very capable photonics person at NIST that there could be better ways to confine the B1 field in a small volume. And this is one of the ideas he suggested, which is to use the anapole. So the anapole, so we are talking about the radiating electric dipole, the oscillating electric dipole. And so what the anapole does is it introduces a new quantity, which is the toroidal moment, and the destructive interference between the toroidal and the dipole, electrical dipole moment, leads to intrinsic diminishing of radiative losses, and that it leads to really high Q factors. So now let's go to the caveats. The first is that over here you see the reported structures are arrays, so they are arrays of 100, tens of coupled resonators, and this coupling increases the Q factor. This is not a good idea for EPR because we want to have a well-defined single spot at which we can place the sample. We can't just put, for example, an aqueous sample over the array because it's going to interact with the electric field regions, and it's going to, and that's not good because water is lossy. Okay, so this is the anapole, and the great thing about this design is that what they have done is they have taken the anapole concept and implemented it in a flat structure. So the flat structure can now be reproduced in a photolithographically deposited metal film on a dielectric substrate. So here we go. Here's our anapole. So the device requirements, as I said earlier, is that we should have a single spot where we can place the sample. We should have good separation between the magnetic and electric oscillating fields, and we should have strong coupling to the microwave feed line. So we need a pretty decent Q factor for this purpose. Okay, so that anapole is is a design that concentrates the electric field in a very small region at the center of the resonator. What we want is to concentrate the excitation magnetic field at the center of the resonator so that we can place our sample over there. That's going to be our active volume. And so we struggled with this for a while, but then someone suggested that we could invert the metal and dielectric coverage. So for example, in the diagram in the middle, in the schematic, in the little cartoon in the middle, the yellow area is metal and the white area is dielectric. And so what we have is a bridge at the center of the resonator, and you have a B1 perpendicular to this bridge, which acts as the active volume. And so we use the Babinets principle to make an inverse anopole resonator. Okay, so we have now a design which has a single well-defined B1, which has great separation between the B1 and E1. And well, let's see if we can couple it to a microwave feed line. I don't know. We'll address this in a future slide. Okay, so this was the next challenge that we came across. That we didn't know how, we started by just placing the microresonator on the microstrip and nothing was really happening. And then what we did was we basically turned the microresonator by a certain angle, by a small angle. So instead of having the capacitive gap in the middle be parallel to the microstrip, we turned it so that it's at an angle of somewhere between 10 to 20 degrees. And when you do that, you get, and then we realized that you can use this turning and the X and Y coordinates to essentially control the coupling between the microresonator and the microstrip. And this is extremely easy to do. So now you have a microresonator that can couple to the microstrip, and it's really fantastic. It's very easy once you learn how to do it. So you can see the difference between the uncoupled and coupled positions, and it shows you the critically coupled position over here in figure C. The Y is basically the vertical offset of delta Y is the vertical offset from the central conductor or the microstrip. X is the distance along the direction of propagation in the microstrip, and theta is how much you're going to turn the microresonator. And so what this allows us to do is you can go pretty much through any state from undercoupled to overcoupled simply by adjusting delta Y and theta. So this is a pretty cool demonstration. This is a simulation, but we can see it in experiments. Okay, so if we change Y and theta, you can change the coupling, but if you change X, you can actually change the resonant frequency. So you have pretty flexible frequency tuning as well, and the range can be several hundreds of gigahertz. So we have now a resonator that can be easily coupled to a microstrip. The coupling can be changed very easily by changing the position of the microresonator on the microstrip. You can overcouple, undercouple, you can critically couple. And you can even change the resonant frequency by shifting the microresonator in the direction of propagation of the microwave. And so we've had this microresonator microstrip device, and we put modulation coils around it, and now we have a device that can be plugged into an EPR spectrometer without really needing external, any other supporting instrumentation. We have reported the solid sample in the paper. So these are some new results on liquid samples. So this is pretty crude. It's basically a piece of a Teflon tube, and I've put about a microliter. It can be much less than a microliter. It's just that it's easier to transfer a microliter into a plastic tube. And so we place a liquid sample into a plastic tube, and we place the plastic tube so that the liquid is in contact with the microresonator surface. And that's really, that's all you need to measure the liquid sample. And if you can make sure, and we are working on more sophisticated microfluidic devices, we're not going to sort of relegate all solution state measurements to, Teflon tubes. But this is just to demonstrate the concentration sensitivity. And so you can see, so in the third and fourth spectra, the phase, I didn't have time to adjust the phase very well, but you can see that we get concentration sensitivity down to 1 micromolar. And this is for a sub-microliter sample volume. This is on LSAT. This is gold deposited on LSAT. Okay, so the second challenge that I mentioned is the scalability. The design should be scalable over a broad range of frequencies. So let's go back to our metal film on the dielectric substrate. So what the planar inverse anapole allows you to do is decouple the resonant frequency from the active volume. So in typical loop gap resonators, you basically keep decreasing the size of the loop as you go to higher frequencies, because at higher frequencies, the self-resonant loop is going to have to be smaller. And so the resonant frequency is coupled to the active volume, and there's really no way to decouple them. Over here, we have a central region, which is the active volume. And we have the resonant frequency, which is determined by the outer diameter. And then you can fine tune it using other parameters, such as the inner diameter, the capacitive gap, and so forth. But basically, now we have decoupled the active volume from the resonant frequency. And so what that allows us to do is make resonators at pretty much any frequency range going for. So here is an example of a resonator at 5 gigahertz, 10 gigahertz, and 35 gigahertz with their dimensions. So this is a very scalable design. These are the microresonator characteristics that were reported in the paper. You get pretty high conversion efficiencies, ranging from 30 Gauss to more than 100 Gauss. And the mode volumes can also range from 100 picoliters to much larger, it depends on how you design the hotspot. The third challenge is, how do we control confinement? And here again, because we have decoupled the active volume from the resonant frequency. Okay, I'm going to start with the first two designs, hotspot designs, that were reported in the paper in 2020. So there are two different designs. They give a very high B1 at the center of the resonator. But a problem is that the B1 homogeneity is very poor, because the sample is going to extend over several hundreds of microns around the hotspot. So if you have even weak B1 in that sample space, that is going to contribute to your signal. So the B1 homogeneity is not very great in these or in any microresonator really. But there are ways. So because the hotspot that central bridge is so small compared to the resonator size, the overall resonator size, any changes in it are a small perturbation to the anapole. And so there's a lot of flexibility in how you can design that hotspot. So over here, for example, I've placed a loop, and that spreads out the B1, and it makes it more homogeneous. And then on the right side is an interdigitated design, and that also spreads out the B1 from an extent of 10 microns to an extent of, this is about 100 microns. And so you can play around with these parameters to optimize your B1 and your B1 homogeneity. So you can tailor the hotspot because it is to a large extent independent of the resonant frequency and the Q factor. And lastly, the material and fabrication requirements. So many of these resonators are made on, they're either superconducting resonators and only applicable at very low temperatures, or they're made at, they're deposited on low loss substrates. So these low loss substrates are usually substrates like LSAT or lanthanum aluminate, or some tantalate or something, and they're very expensive substrates. And so the cost can be prohibitive in terms of materials. But in the past few weeks, what we have done is we've made these resonators on fused silica. So for example, a 3-inch LSAT substrate will cost around $500. This is a 4-inch. Actually, a 2-inch LSAT substrate will cost around $500. This is a 4-inch fused silica substrate. It costs $60. So you can sort of estimate, that the resonator, in terms of material requirements, the resonator becomes very cheap. It becomes pretty much disposable, so that you can make many resonators. And once you put the sample on the resonator, now you don't have to worry about it. Now it's just the sample and the resonator. And then you can use that. So basically, when you're replacing the sample, just replace the resonator chip. These resonators surprisingly also give a concentration sensitivity of approaching 1 micromolar per 1 micromolar. I didn't have time to put that concentration sensitivity data over here, but here it is. So in conclusion, microresonators confine the excitation field B1 to very small volumes. But for EPR operation, there are some specific requirements, which is that your sample volume needs to be a well-defined single spot, which is well separated from the electric field. And resonator design now is not just about now we should think of it not just as confining the B1 field to a point, but actually tailoring the shape of the excitation field to match, either if you have a thin film sample, then we can start thinking about, for example, that interdigitated design might work better. For a solution sample that requires B1 homogeneity, the loop might work better. For a sub-picoliter size sample, we might want to go to a very small hotspot that's even smaller, that has dimensions in hundreds of nanometers, so that it creates a very strong region of very strong B1 over a very small volume, so that it can be detectable. This is something that I haven't achieved yet, but we're working on it. So sub-picoliter volumes are quite challenging. And lastly, the resonator should be scalable and cost-effective, especially if we are thinking about using it in a compact spectrometer or a portable spectrometer. Then it needs to be. You need to be able to make many of these, and they should be more or less disposable. You can't have expensive substrates, and we have done that by using fused silica. And this is a summary of the work that we've been doing so far. Veronica is my mentor. We talk about everything. She's a fantastic mentor. And I really can't say enough. Amit has been so great in helping me with so many things. And he provided us with the idea of the nanopole. Bob McMichael is a mentor again, and he taught me. I always go to him with all sorts of questions about RF engineering. Jason and Pragya, they helped me get the first signals from these microresonators. And I have really great collaborators here in NIST, and it's such a pleasure to work with them. The machining and fabrication work on this project was done by Alan, Dave Glenn, and Steve. I'm funded currently by NIH, and I'm also funded by PML. So with that, I open the talk to questions. I apologize if I hurried through some things, but please feel free to ask me any questions that might have occurred to you. Thank you.
Thank you, Nandita. That was pretty great. Just imagining the possibilities of how to implement that. I think like other people probably gonna, if you have a question, you can either type in the chat, raise your hand, or just interrupt. Feel free to just interrupt. I'm just gonna go ahead with not really a question, just kind of like an idea. I mean, this is kind of amazing that we are so small now that you can go with such a small volume. And like thinking about pharmaceutical industry, when one has a protein, we obviously want to make EPR applicable to pharmaceutical industry and everything, because everybody should do a little EPR. Why else are we here? So it would be awesome if one had just like a well plate with each one as like a little resonator or something in there, and then you could just detect, just squirt in like thousands of substrate, just detect, because this should be possible. What you have shown, is that something to think about, or are you guys thinking about it already?
We have talked about high throughput EPR and so forth, but nothing concrete. It's, right now it's just a pie in the sky idea. But I mean, yes, I think it is within the realm of possibility.
Right. I mean, this is going to be great. I mean, yeah, better than Fred. All right.
I have a question.
Yeah, go ahead.
Okay, so first of all, I agree with Thomas. Even though it's a pie in the sky, we too sometimes get this kind of request. I show some, curated EPR spectra. Some of my biology colleagues get really excited and ask, can we do that on a bigger scale, for screening. So I agree that that would be a nice pie in the sky to aim for. I have a couple questions. Let me start with a practical and maybe a less practical question. One is, did I understand it right, that because it's a microresonator that in principle could be made disposable, that if one had very, let's say, air sensitive samples, that you can prepare them in the glove box with the sample, seal the whole thing somehow, and then take it out and basically put it in the EVR spectrometer, because that's always a problem of how do we handle air sensitive sample.
Yeah, that's an engineering problem, but I think that's definitely possible. And I think one of the problems that, or one of the changes that we might have to make in the device is, right now it's coupled to the microstrip, but for an application like that, maybe we might want to think about coupling it to the microwave source in some other way. Maybe put edge launch connectors on the microresonator or something, so that it can be directly wired to the bridge.
I'll ask just one more practical question and then I'll let others ask. So I think you also said, you showed that you already implemented this idea in an existing EPR spectrometer, but many of us have here existing X-band and Q-band or spectrometers. What does it take to implement your group structure into the existing system?
Yeah, so the first thing is that you should have you need to put a set of modulation coils, but these are air core coils that that are very cheap. They cost about $50 at the most. The second thing is that so with the Bruker instrument, for example, the modulation coil calibration really affected our ability to detect signals. So you have to figure out a way to do the calibration on the spectrometer. And once the calibration is done, it's pretty robust. And that's the only, and the third thing is, in the Bruker spectrometer, so even though I see a nice sharp dip on the VNA, we don't see the same thing in the Bruker sort of display, because probably because it's too narrow. But so you can't use AFC in that case. But then what we do is we just go to the frequency locked setting, and then that's all you need, and then you're good. You're good to go.
I see a question in the chat, Thomas, by Mikhail.
Yeah.
Can I just add one thing, Sung-Yi,
sure.
just real quick? So
ahead,
one thing is that you do need a vector network analyzer to do the placement of the microresonator. So you do need to sort of assess it before you move the assembly into the spectrometer. So that is one other piece of equipment that you kind of need to have to be able to make this work.
Yes,
that's a fantastic point.
Tune and match basically picture.
Exactly.
Yeah,
exactly.
Yeah.
I think luckily there are some people on the call, they are working on this kind of development too. So yeah, great point.
Mikhail Kern had a couple of questions. Mikhail, do you want to ask that in person, or otherwise I go ahead?
Sure, I can do.
Great, thank you.
Displays.
Yeah.
It's a lot of questions, so we don't have to go through all of them based on the time, but first, thanks for the cool talk. It was super interesting. The first question would be, how far does the B1 extend into the Z direction?
Yeah, so the Z extent is typically proportional to the size of the hotspot itself. So if we confine the B1 to, let's say, a hotspot of 1 or 2 microns by 2 microns, then the Z1 is also confined to the same degree. As we make it larger, the Z extent also increases. So proportionally to the size of the hotspot.
And if you would then have a solution, for example, like you had the tube filled, then this means the sample would see quite an inhomogeneous B1, no, in this direction, or not?
Yes, it would. In the Z direction, it would. And that's right. But you can control that to a certain extent by controlling the volume of the sample itself.
And then you mentioned that you are basically aligning this by hand, right? So
yes.
How sensitive or reproducible, is it to critically couple?
I can do it pretty quickly. Okay. I make the resonators and I can couple them. For a new person, it might take some practice, but once you get the hang of it, it's super easy.
So I've done it, Michael. I've done it. This is Veronica. Yeah. I've done it So it's not too hard, really, honestly, and I'm not the person who
All
makes
right.
these.
So it's not like you misalign by a millidegree and it's completely off.
No.
So the way you
No.
stop that from happening is you adhere the microresonator using some sort of grease.
Mhm.
That keeps it pretty. That's good enough to keep it.
Couldn't we just copy like design from NMR where we just have a match, a rod, and then we just turn it a little bit? Then you don't need to bother about the hand at all anymore. Just have a match rod.
Yeah. So yes, and we thought about that, but I was told by Glenn, who is our machinist extraordinaire, that if you change the length of that rod, the longer you make it, the more error there is in the positioning. So if you want to change it on a micron scale, then it becomes difficult.
Okay.
So you have to have, you could probably do it using a micro manipulator, and that would be a more rigorous way of doing it. But right now I'm just shuffling the resonators by hand.
So the actually like what in the pictures what you had, that was actually the grease, right? Because I noticed it was like a wavy stuff.
That was
okay.
grease. Yes.
I was wondering. All right, sorry.
Yeah, and the third related question to this is, if you would now cool the system down, I imagine the angle would change a little bit, so we'll have to adjust it somehow afterwards, right?
Yes.
So the micro manipulator might be a good, good thing to have there.
So I mean, in this regard, like, I mean, then, because right now we only talk largely about CW, right? But then you could use those resonators easily for pulse as well, and they should be way more sensitive than whatever we have right now. Is that correct?
But as I said, the main problem with any microresonator is the P1 inhomogeneity. But yeah, there are ways to solve it. So like I showed, the loop design of the hotspot and the interdigitated design. It's so those are just in the simulation stage right now. I haven't made them or tested them yet. So.
Because in theory, if you go small enough in volume, then you can increase the temperature, and you can still do good pulse on that.
Yeah, then yes, absolutely. Then it becomes a matter of, is your B1 strong enough within that volume to be able to detect that small signal?
Right.
Yeah, but you can,
So then we would just go forward towards actually measuring deer like closer to temperature which are actually usable, and don't have the argument like, oh yeah, well, we can't do it at room temperature kind of argument. So that's cool.
I have another question. So about pulsed, and this is me being naive, I don't know, but beside, even with your current one, there are two questions. One is, if you have the structure because of the B1 inhomogeneity, if you know it, can you in principle just account for it computationally and basically back calculate your signal?
I have been told that you can do that using an AWG and by using shaped pulses.
I think Veronica said
but
something.
I don't know. Yeah.
So she didn't tell you this, but with the 34 gigahertz resonators, we have gotten echoes out of them. So without doing very much to optimize, without using shaped pulses to account for the B1 inhomogeneity, we have been able to get echoes out of her 34 gigahertz samples with our NIST-built spectrometer. So not
but if you get an echo, then you could just measure T1s and T2s already, right? I mean, that should not be a big deal then. Is that correct, Veronica?
Yep.
So did you measure it?
No,
we haven't,
not yet.
We haven't gotten around to it.
Oh, that's gonna be exciting. Ha! Great. Oh man. Does anybody else have some question for Nandita? So, just curiosity. I mean, because it's so small, and I mean, all of us want to use those tabletop EPR spectrometers. I mean, especially for CW. In a way, we can go like to pretty much phone size, right? It's just the magnet which we still need. But if we use an electric magnet, I mean, we can go bigger and bigger with smaller sizes. So you can, I mean, you don't even need to think about a benchtop anymore. I mean, in reality, I mean, it's like carry along EPR spectrometer. Is that correct to assume? So what?
I can certainly envision it.
What's the smallest size you can imagine going? Not like resonator, but actually the whole thing, the whole package.
So the B1 extent is in the hundreds of microns. So we need only a static field homogeneity of that range. And so if we can reduce the magnet size to that by that degree proportionally, and I mean, I don't want to say too much, but we could play with the idea of, integrated circuits and, detection components added to the resonator. But yeah, I don't want to overstate anything, but yes, it is a vision that could be visible.
Well, I think Nandita, one other thing to say is that you could use a permanent magnet if you don't need to sweep very much, right? So if you only need to sweep to see radicals, you don't need a large sort of sweep width to be able to detect those. So you can go to these little permanent magnets.
Yeah, absolutely.
Would really reduce everything, right?
Yeah, exactly. Yeah, that's exactly the sort of motivation behind the compact spectrometers that we talked about earlier, that you can use permanent magnets because the B0 stringency requirements, like the B0 requirements, homogeneity requirements are not that stringent.
Before we, I know it's a very exciting talk. Before people are leaving, let me just share really fast the upcoming presentation. Just, we can keep talking. The next presentation will be Michael Kern on hybrid spintronic materials from conducting polymers with molecular quantum bits. So please, that one was wrong. Anyway, so please join in and wait for our email to come out, and then we figure everything out. All right. Thank you very much. But so now you can keep talking. Sorry about that. I just want to make sure other people see it.
Thank you so much for the opportunity to present today. I should have mentioned that much earlier.
Oh, that's all right. Thank you very much. Anybody else has some more questions before we conclude? All right. Thank you very much, and I see you next time for Mikhail's talk in 2 weeks from now. Thank you.
The video recording will be uploaded to the IES website, probably later today or tomorrow.
And Veronica, nice to hear you again. That's been a long time. So
sorry,
I didn't see you, but happy to hear you.
Thank you.
All right. Anyone else has any questions? No? Okay.
Thank you.
Goodbye, everyone.
Okay.
Bye.
All right.
Bye.
Sanji, you still want to talk? I
Yeah,
have
we can.
7 minutes.
We can just a few minutes after organizational. So.
Yeah. Okay. I have 7 minutes. we have let me stop recording first.
Oh, that for sure. That for sure. And then we can.